know that little date stamped on every medicine bottle? We've all seen it. We know we're supposed to pay attention to it, but what does it really mean? Is it just a suggestion? A hard and fast deadline? Well, today we're going to dive in and find out what that date is all about. It turns out that simple little date is actually the very last step in a massive global process. It's this incredible combination of science, super rigorous testing, and international regulation. It's not a guess, it's a scientific promise. So how on earth do they make that promise, and how can we be so sure it's one we can trust? Okay, so the official term for what that date represents is the shelf life. Basically, it's the period of time, starting from the day it was made, that the drug is guaranteed to be safe and effective. That means it's going to do what it's supposed to do without causing any unexpected harm. It's a promise, but it's a promise that only holds if you store it the right way. So to figure out that shelf life, scientists can't just, sit around for 5 years and see what happens. That would take forever. They have to predict the future. And to do that, they use a process called stability testing, which is kind of like putting the medicine into a scientific time machine. And these time machines are actually called stability chambers. They're basically these highly controlled environments where scientists can crank up the heat and humidity to deliberately speed up the natural process of degradation. By doing this, they can see what years of sitting on your shelf would do to a drug in just a matter of months. Pretty cool, right?
The whole process is incredibly methodical, as you'd imagine. First, they put a bunch of samples into the chambers and set the conditions just right. Then, at very specific intervals, they call these time points, they pull out some samples for a full workup. They take them to the lab and test them against the original specs to see exactly what's changed. And check out how specific these conditions are. For what they call long-term testing, which is meant to mimic real-world storage, the global standard is precisely 25 degrees Celsius, that's about 77 Fahrenheit, and exactly 60% relative humidity. This isn't some casual tests in a warm room. It's a globally recognized standard designed to cover storage conditions in many, many parts of the world. And they don't just check it once and call it a day. Nope. They test the samples right at the very beginning to get a baseline. Then they pull more samples at 3 months, 6 months, a year, 2 years, sometimes for up to 5 years or even longer. This creates this incredibly detailed map of how the drug holds up over a long period of time. So when the scientists pull these samples out for testing, what are they actually looking for? Well, they're basically detectives, searching for clues about the drug's quality. And these clues can be broken down into 3 key areas, which I like to call the 3 Ps. First up is potency. Is the medicine still strong enough to actually work? The second is physical characteristics. Has the pill changed color? Has it gotten too hard or too crumbly? And finally, there's purity. Has the drug started to break down into other chemical compounds that could potentially be harmful? All 3 of these have to stay within really strict limits. Now, this is the really critical part, especially for potency. Generally, a drug is considered expired once its active ingredient drops below 90% of the amount that's printed on the label. That 10% drop, that's the line in the sand. It's the difference between a medicine that's effective and one that you just can't trust to do its job anymore. In the world of pharmaceuticals, this whole concept is so important that it actually has its own name, T10%. And it means exactly what it sounds like. It's the measurement of how long it takes for 10% of the drug to degrade. That value is the golden piece of data they use to officially set the shelf life and ultimately stamp that date on the bottle. Okay, so we know what they test for, but how do they use data from just a few months of this accelerated testing to predict years and years of stability? Well, the answer lies in a fascinating field of chemistry that's all about how fast things change. That field is called chemical kinetics, which is really just a fancy way of saying the study of how fast reactions happen. By measuring exactly how quickly a drug breaks down under stressful conditions, like in a really hot chamber, scientists can create a mathematical model of its behavior. And that model lets them reliably predict how that same drug will behave under normal room temperature conditions over a much, much longer time.
And this is where the magic of math really comes in. The key tool they use is an equation called the Arrhenius equation. Now, you don't have to be a math whiz to get this. All you need to know is that this formula perfectly connects temperature to the speed of a chemical reaction. By plugging in the data from those hot stability chambers, scientists can confidently calculate a shelf life for normal storage. It's the mathematical engine that makes the whole prediction possible. Now, this entire process isn't just happening in some random lab. To make sure that a medicine made in one country is safe to use in a completely different country, the whole world has basically agreed to follow the same playbook. This is what creates a global safety net for all of us. And that playbook is written by the International Council for Harmonization, or the ICH. They create these unified guidelines that regulators in the US, Europe, Japan, and many other countries all agree to follow. They've even divided the entire world into different climatic zones, which ensures that a drug is tested for the specific heat and humidity of the region where it's actually going to be sold. Now, just imagine a drug that comes in 5 different strengths and 3 different bottle sizes. Testing every single combination at every single time point would be a logistical nightmare. So the ICH allows for some smart, science-backed shortcuts. With bracketing, you only have to test the extremes, like the weakest and the strongest dose. And the assumption is that everything in the middle will be stable. And with matrixing, you test a different strategic handful of samples at each time point. Both methods help reduce the insane amount of testing without sacrificing the quality of the data. So we've gone all the way from the bottle in your caveat through scientific time machines and all the way to global regulations. But let's bring it back home. Why does this incredibly complex, expensive, and time-consuming process matter so much? Because the consequences of getting this wrong are serious. An unstable drug might lose its potency, which means you're not getting the medicine you need. It could change in a way that your body can't absorb it correctly anymore. And worst of all, it could break down into new compounds that are actually toxic. That date isn't just about whether the drug works, it's fundamentally about whether it's safe. So the next time you look at that date, don't see it as just some suggestion. See it for what it really is, a scientific guarantee. It's the final result of this immense global effort, all designed to give you and me and all of us confidence that what's inside that package is safe, it's pure, and it's going to work exactly like it's supposed to. And that really brings us to the future, doesn't it? As medicines get more and more complex, we're talking about biologic drugs, gene therapies, the science of stability testing has to evolve right along with them. So it leaves us with this final question. What new kinds of time machines and what new tests will scientists need to invent to keep making that vital promise on the package?